The topic that I'm going to take today is current source inverters. As the name suggests, current source inverters are those inverters which are fed by a constant current source at the input side. Like in earlier studies, we discussed about VSIs. In VSIs, the input voltage is supplied through a constant voltage source. Generally, it is a battery. So battery is considered to be a constant voltage source. So in VSIs, the input voltage is maintained constant and the amplitude of the output voltage does not depend upon the load. So whatever is the input voltage, the same is available at the output, but the polarity gets changed from DC, it gets shifted to AC. But the magnitude of the output voltage, it is not dependent upon the load. However, the load current has its magnitude dependent upon the load. So current is dependent upon the load, but the voltage waveform is not dependent. This is the case of the VSI that we have studied till now. In current source inverters, what happens? In current source inverter, the input current is constant, although it is adjustable, but it is constant. It is supplied through a source which gives you a stiff current at the input, and that current will appear at the output with the change in direction. However, the magnitude of the output current in case of a CSI is not dependent upon the load. The magnitude of the output voltage shall be dependent upon the load. So this current source inverter is totally opposite to a voltage source inverter. Now in current source inverter, these there are some differences which you could make out between a VSI and a CSI. In CSI, you will find at the input side there is an L filter connected. This L filter, it removes out the ripples from the current. However, in a voltage source inverter, you will find a capacitor at the input side. The purpose of the capacitor at input side in case of a VSI is to filter out the ripples in the input DC voltage. Whereas in a current source inverter, at the input with the source in series with the source, you will find an L connected, an inductance connected, and this inductance filters out the ripples contained in the current. The frequency of AC current, whatever output you are getting from a current source inverter, its frequency will depend upon the switching rate of the SCRs. The amplitude of the AC output current can be adjusted by controlling the magnitude of the input current. Now, as I said, in case of a CSI, current source inverter, the output current is not dependent upon load. So, with what will you do if you wish to vary the output current? To vary the output current, there is only one way. It can be adjusted by controlling the magnitude of the DC input current. So unless you change the DC input current, the output current will not change. However, the output voltage may change, or the output voltage waveform and its magnitude will totally depend upon the kind of load it is having. While the case in case of VSI, this is different. In case of VSI, the output voltage is dependent upon input voltage. However, the output current depends upon the load. Now, a CSI does not require any feedback diodes. However, feedback diodes are required in voltage source inverters. In this, you will learn that feedback diodes are not required here. Commutation circuit is simple as it contains only capacitors. You will find in current source inverters, we use capacitor. These capacitor provides the commutation to the thyristor. So we need not to have the bulky commutation circuits as we used to have in a VSI. As power semiconductors in CSI have to withstand reverse voltage, devices such as GTO, power transistors, power MOSFETs cannot be used in a CSI. You will invariably find that the CSIs are structured with the help of they are designed and made with the help of the thyristors. So the switching devices used in the CSIs are mostly the thyristors, that is the SCRs. These are the applications, the typical applications of current source inverters. They are used in speed control of AC motors, induction heating, lagging VR compensation, and for the synchronous motor starting. This is the basic circuit which shows the working of a current source inverter. Now here we have made one assumption. That assumption is that the switches that we have used, the thyristors here are considered as lossless, and they are considered to have the zero commutation time. That means if they are switched on, immediately they will come to the on position, and when they are turned off, they will immediately go to the off position. So commutation time is taken as zero, and this figure, whatever directions we have taken here, like if it is positive and negative, this current direction, all these correct directions which are shown here are considered as the positive directions. Now let us see how it works. This is the output waveform. If you switch on T1 and T2, when T1 and T2 are switched on, this input is this input gets connected to the load, and this connection is established through this inductor, then T1, then load, and then through T2, and then back to supply. Now please mind it, the source is a constant current source. That is why during 0 to T by 2, this is the time during which thyristors T1 and T2 are on. During this time, the output current is equal to I. It is similar as the input current. Now the output current is similar and it is constant. When at this point T by 2, thyristors T1 and T3, when these two thyristors are switched on, T1 and T2 goes out of service, and at this time the load gets connected in reverse direction. Like this, I now flows through T3, then T3 through lower terminal of the load, then to the upper terminal of the load, and then through T4 it goes back. So at the output side the current gets reversed. However, the current I at the input side is similar. So for 0 to T by 2 we get a positive current, from T by 2 to T we get a negative current out at the output. Now alternatively, if you keep on switching these two pairs, T1 T2 and T3 T4, you will get this type of output current. Now let us see what happens to the voltage. Let us for the time being consider that the load is capacitive load. Now if the load is capacitive, that means the current I naught, it is given by a relation I naught is equal to C dV by dt. Now we have considered, because it is a current source inverter, the I naught will be constant. So if I naught is constant and C is constant, that means the change in voltage dV by dt should also be constant. So during this time, what happens? The voltage changes from this negative value to this positive value, and this changes a linear. As I naught is constant, the slope dV naught by dt is also constant over every half cycle. Now this slope is positive from 0 to T by 2, and this slope is negative from T by 2 to T. So this is the output voltage. This output voltage and this current, they have this as the phase angle, and this angle exists because of the load. Now this output voltage, if you carefully look at the output voltage, you will be able to find out the wave shape of the input. Now in a current source inverter, the devices that we have used, these four devices are unidirectional devices. Now because the devices are unidirectional, the output voltage and the input voltage will have a relation. What relation it will have? During the first half cycle, that means from 0 to T by 2, the output voltage and the input voltage will be same. That is, V input will be same as the V output when thyristors T1 and T2 are conducting. But during T3 and T4, the input voltage V in will be minus of V naught. So if this is the slope for V naught, then the V in will be opposite to it. That means the V in will have this waveform. So if you compare these two waveforms, you will find that the frequency of this waveform, the output waveform, has a frequency of f, while the input waveform is having a frequency of 2f. Now this is the frequency. Now DC current input to a current source inverter is unidirectional. So if the average value of V input is positive, the power flows from source to load. If if the input voltage is positive, the power will flow from source to load, and if this voltage is negative, the power will flow from load to source, and during this time the regeneration will take place. Now this is how a CSI works. Let us take a case let us take a case of single phase capacitor commutated current source inverter. Now in this inverter at the load we have connected a capacitor in parallel with R. Now when the load is like this, then see how a single phase capacitor commutated current source inverter works. Now here this is a current source I. This I is supposed to flow through either T1 or T3. Now let us say at this time, at time 0, let us say thyristor T1 and T2 are fired. So when T1 and T2 are fired, the circuit will be connected like T1 and then through this combination and then through T2, and it will be back. And the current will remain I. To up till point A, the current is I, and at point B, the current which is leaving from this point will also be I. So this is the current I which is flowing through the load side. Now we have to see what is the value of current IC, what will be the output voltage, what will be the load current. Let us see through these waveforms. Now look at this point at t equals to 0. At point t equals to 0, the initial condition of the capacitor is taken as this plate as negative and right plate as positive. So at time t equals to 0, at time t equals to 0, the left side of the capacitor is taken as negative and right side of the capacitor is taken as positive. Now at this time, what happens? During this time, this capacitor, because it is charged with a negative voltage, it is this voltage minus V1. The voltage of the capacitor is negative V1, and this is the voltage which is appearing at the load. So we can say that V0, the voltage at the load, is nothing else but V1. So this minus V1 is the output voltage, and this minus V1 is also the voltage of the capacitor. Now here we have considered the load to be resistive, so that is why the voltage and the current will have the same waveform. Now here this voltage is negative. When thyristor T1 and T2 are fired, what happens? A current gets established in this circuit through this capacitor and through this resistance R, and then it goes back to supply like this. Now here the capacitor current IC at time t equals to 0. Now capacitor voltage is negative, but its current is given by I plus I1. Now what is I? I is the current that is coming from this, and there is one more current I1. This current I1 is V1 by R. So there are two components of current which are flowing through the capacitor. Now this is the initial current that will flow through the capacitor, because at time t equals to 0, the capacitor is considered to be a short circuit. So if it is considered to be a short circuit, that means this current I would be flowing through the capacitor, and whatever is the capacitor current which is discharging through this resistance, that is also flowing through this capacitor. So at time t equals to 0, the current of the capacitor is I plus I1. Now this capacitor, because it is having a polarity of negative here and positive here, so during the first half cycle, when T1 and T2 are conducting, this thyristor, this capacitor, it first discharges, and when it completely discharges here, then again it starts charging in the reverse direction. So during this first half, the capacitor first discharges and then it gets charged with the opposite polarity, and when it gets fully charged at this point, the voltage of the capacitor will have this polarity. At this time, in between this time, the capacitor current is continuously decreasing. Why it is decreasing? Because the capacitor will first discharge and then it will charge in the opposite direction. So during this time, because during the charging and discharging cycles of the capacitor, the current the current which is taken from the supply, although with respect to this capacitor, this current earlier it was negative and then it became positive, but this current I, since it is flowing through this route of this capacitor, so that is why it is shown it is continuously decaying, and this current decays, it does not touch zero, rather this decays up till I minus I1. Now this is the point when the current I is also when the capacitor current is reduced from I plus I1 to I minus I1. Why? Because I1 earlier it was negative here, and here the direction of current is completely reverse. So earlier also it is the current I plus I1 which was flowing through the capacitor. Here also it is the same, but because the direction of current I1 is reversed, that is why we are writing it I minus I1. Now this is the time when thyristor T1 and T2 goes out, and this is the time when thyristors T3 and T4 are fired. When T3 and T4 are fired, at this time the capacitor is having this polarity. And when the capacitor is having this polarity, that means the capacitor is now discharging in this direction. So that means the discharge current of the current IC is now reversed. And because the load is connected to T3 and this current I is entering from this side, so this will also reverse the direction of current C. So that is why immediately at this time, the direction of current will reverse through the capacitor and it will attain a value of I plus I1 in the reverse direction. That is why we have made it negative. Now again, the similar cycle will repeat. The capacitor will now discharge in this direction, and then again it will charge in the negative direction, and during this the current will be completely discharging. This current will discharge from I plus 1 to I minus I1, and the same cycle will repeat. This input voltage waveform, it can be taken through V0, as we discussed in the previous case. The voltage Vin will be equal to V0 from 0 to T by 2. So during this time, this input voltage will have the same waveform as the output voltage, but from T2 to T. That means for this duration of time, the input voltage will be opposite to the V0, because V0 has reversed at the load side. But because of the unidirectional switches, it cannot reverse. The voltage input cannot reverse. That is why from 0 to T by 2, Vin is equal to, from 0 to T by 2, Vin is equal to V0, and from T by 2 to T, Vin is equal to minus V0. That is why during this time, this is just reverse of this waveform, and the cycle continues. Here again, it could be noticed that the frequency of the input voltage is double compared to the frequency of the output voltage. Now here you can see there is no commutation circuit involved. We have not used anything extra other than this capacitor to turn off these thyristors. There is one more kind of this current source inverter which is available. This is called single phase auto-sequential commutated inverter. This is the most common CSI which is in use. Now in this CSI, we have the four devices: T1, T2, T1, T2, T3 and T4. T1 and T2 will be fired at one time, and T3 and T4 will be fired at one time. Now this is the point. Let us see at time t equals to 0 what happens when T1 and T2 are fired. When T1 and T2 are fired here, the current, this input current I, it gets connected to the load via this circuit T1. Now this capacitor is assumed to have this polarity negative at this side and positive at this side. This is the initial condition of the capacitor. Now when current enters through T1, then it enters this capacitor, then through D3 it connects to the load. Now why at this time D3 is conducting and D1 is not conducting? Because this capacitor is having this plate as negative. This negative creates a negative bias for this diode D1, whereas this positive makes this D3 as forward bias. That is why when we switch on T1 and T2, it is the diode D3 which becomes forward biased, while this D1 becomes reverse biased because of the polarity of this capacitor. That is why the current establishes through T1, then through this capacitor, then through D3, then through this load, and then through D4, and then this capacitor again. This is assumed to be charged with this initial condition. This is negative, this is positive, and this negative is making this D4 as forward biased. This positive is making D2 as reverse biased. That is why D2 is not conducting, and then the current enters this capacitor and leaves via T2, and from here it goes back. Now during this time, this is the time t equals to 0. Now as long as we keep this T1 and T2 as closed, during this time what will happen, this capacitor, it will first discharge. Similar way, whatever will happen to this capacitor, simultaneously that will happen to this capacitor as well. Both of these capacitor will charge and discharge simultaneously. So if this capacitor, if current I is entering in this capacitor will first discharge. This discharge is shown from here. This is the capacitor voltage. This capacitor's voltage is shown to be negative at time t equals to 0. This capacitor will first discharge. So this is the time t1. During time t1, the capacitor will first discharge. And during time t2, this is the time t2. During the time t2, the capacitor will charge. So this discharging and charging of this capacitor will happen in time t1 and t2. When the capacitor is discharging, the output current is I. When the capacitor starts charging, when the capacitor, first of all, this capacitor will first discharge. This is the point when the capacitor is completely discharged. When the capacitor is completely discharged, at that time what happens? When the capacitor gets discharged, this negative bias which was coming at D1, it vanishes, and this D3, this positive to the D3 also vanishes. So at this time, because its polarity is 0, now after this point, the polarity of this side, of the left side, it starts becoming positive and this starts becoming negative. So what happens after this time? At this particular time, this diode D1, it also comes into conduction. When D1 comes into conduction, similar way from here, D2 comes into conduction. So this is a small time T2 during which diode D1 is conducting, and from here diode D3 is also conducting. So soon this current which was earlier flowing through D1, which was earlier flowing through D3, this current, it slowly and gradually it shifts to D1. So as the current through the capacitor, because the capacitor will first discharge and then it will charge, so this current through capacitor, it will go down to 0, and this will make this current id3 as 0, and this current will be shifted to id1, and soon the current through diode d1, it will start rising. So during time t2, the current through D3, it reduces, while the current through D1, it establishes. Now this is how it goes, and then the current continues through ID1. The current continues through ID1, and at this time the load current is also reversed. Now at this time, earlier it was flowing through D3 and then load, so the ultimate current which gets established is through T1, D1, then through this, then T2, D2 and T2. So this is the ultimate direction that happens after the charging and discharging of capacitor happens, and the circuit remains under this mode as long as T1 and T2 are on. During this time the current is negative because we have considered this as the positive direction. So that is why the load current is shown to be negative here. It is the diode D1 which is conducting. Now what happens at this time? This is the time when a firing pulse is given to T3 and T4. So when a firing pulse is given to T3, at that time immediately this current gets transferred to T3. Why? Because the capacitor at this condition is positive at this side and negative at this side. Now because this is positive, T1 is already receiving a negative bias from this. Because it is positive, it is making it reverse biased. So this polarity of the capacitor which is changed here, this capacitor polarity is already making it reverse biased, but because the current is already flowing through T1, the T1 cannot be commutated. So when we trigger T3, immediately at that point the current gets transferred from T1 to T3, and because it is already reverse biased, this immediately opens up, and this is the time when thyristor T1 opens up, it gets commutated. Similar way T2 also gets commutated, and the current then first establishes through T3, then through capacitor, then through load, then through D2, then through capacitor, and then through T4, and then back. So this is the this is the very first condition during which the capacitor charges and discharges. And when the capacitor at this point again, it gets, first it discharges, and then when at this point when it again gets charged in the reverse direction, the ultimately circuit becomes T3, D3, load, D4, T4, and this. So this is the final conduction which happens during the next half cycle. So you can see from this circuit that the thyristors T3 and T4, when they come in at the same time, T1 and T2 gets out of service. So T1 and T2, they automatically gets commutated when T3 and T4 comes in. And similar way, when at this point T1 and T2 are again triggered, T3 and T4 will automatically go out. That is why it is called single phase auto sequential commutated inverter. In this lecture, I have discussed these two types: single phase capacitor commutated CS inverter and single phase auto sequential commutated inverter. We have discussed the single phase inverters only. Let us keep our discussion to single phase for this particular subject. I'll be keeping this discussion to single phase only. However, for the three phase, a similar kind of, like this single phase auto sequential commutated inverter is also available for the three phase. The similar structure will be there. However, the switching times will be different. Well, I think this is enough for current source inverters. Thank you.